Working, I mean, I switched it on.
Yeah, that's right.
Okay, good. Sound without video doesn't do much, does it? Okay. Okay. Okay, so I think we can start slowly. I mean, I'll start with... So I gave this similar course on several occasions, and I was observing the number of students as the course went on. And to my surprise, when I was doing the course on the board, the number of students started being increasing function of number of days. And then actually this is first time I'm doing with the slides. So I need to learn from you about the... what I got as a feedback, the reason why I'm mentioning this, I want in the end of the course, I would like to get some feedback from you in the end, not now. I don't want to get depressed before I finish the course or overly optimistic. So one of the feedbacks I got from the students was that actually when you get the lectures on the board, the speed at which a regular lecturer writes and talks is much closer to the speed of brain being able to process the information. So apparently they acquire more information by following the lectures on the board than on the slides. I don't know if it's true. Maybe it's possible. But I'm saying this is the first time when actually almost whole set of the lectures is on the slides. So it kind of restricts of what I say. When I work on a board, there is a freedom and creativity. I can diverge a bit, but I can't tell you something else which is not on the slides. So I'm bound to kind of repeat even mistakes if they're on the slides. There are no mistakes. So I hope you catch them if they are. So now what I wasn't clear about, so the way it works, it's 9:15 to 11 in the morning, and it's 1:15 to 4 in the afternoon. I think we'll fix 2-2-1, meaning 2 lectures, 2 exercises, and 1 lecture. But again, it's going to be flexible depending on how much gets covered. For the exercises, I do want you to know one thing. It's going to be interactive. It's going to be hands-on. So I'll write down the equations, but then I'll ask you to write the code in this toolbox. It might be a bit tricky first day, but it's going to be very intuitive. The reason why I want you to do this is I want you to see that sometimes actually it's not that I'm lazy, but I thought if I prepare the code and give you the code, what's the joy of it? Not much. I learned the most when I was fixing the problems which were going wrong with the code. That's when you finally, when it starts working the way it should, you're happiest. So I think actually that's the way it's going to go. The thing I didn't tell you, I will be selecting for each of the function, if you will, or each set of the things I want you to code, I'll be selecting prototype code. So the cleanest code will go into my slides. I left 2 sets of slides, and it will go under your name. Okay, so I'll name person so-and-so has contributed this code. And I hope that's going to be okay with you. So it's not going to be a competition. Very likely I'm going to be biased because I like the certain way of writing the things, and people code up things all sorts of differently. So I'm not going to tell you how to name the variables, how to do the loops. That's your thing. I'll just look at the code and see which is the closest to what I think is the cleanest code I'll take. And then actually at later stage you can exchange and use this. The idea of the coding sessions will be that actually you will be able to test these concepts, and eventually, if some of your problems in your PhD studies fit the problem, use the same code for solving these problems. Okay. Now what happens actually if instead of a control system we deal with a system that doesn't have a control, so just dynamics, just dynamical system. It's still constrained, and of course this problem is presumably simpler because there is no decision on our part to take. But still, questions we may want to ask is if we get a closed loop dynamics, and such a system may arise from a control system to which you have applied specific control function. So you have converted to purely dynamics, or closed loop dynamics as they call it. We may still like to know or to say something about safety of this system. So for example, what would be an interesting question if I tell you, okay, my dynamical system evolves according to the rule xk plus 1 is equal f of xk, and this system is constrained to a set x. What would be the question you would like to ask yourself? Don't look at the slide. It's not one-step question. There is a bigger question at stake. So imagine this system represents closed-loop chemical reactor. Okay? And imagine that these constraints mimic the temperature levels. So what would be the first question that would come up to your mind?
Is it stable?
That's a good question. Okay, what would be the... Let's say it's not quite the first question, but it's close to the first question. It's 1.1 question. What's 1.0 question? So if you have a temperature, chemical reactor, what would be the first thing at the stake? It begins with S. Would you like to walk by this reactor if you know that it can explode? So the first thing is safety. So the first thing you would like to ask yourself, is this safe? Now, what would mean, is it safe? It would mean, would it, your system, driven by these dynamics, actually remain all the time within the constraints? So, would our chemical reactor, sorry for taking that example, let's take another example, would our autonomous car drive, obey the regulation imposed by the law, and still never cause an accident? That would be a safety question asked in an autonomous driving setting. For chemical reactor, you can say, will this keep the temperature between the levels? Now, and of course, because this is a process which presumably will run forever, the question of being able to maintain the temperature over 1, 2, 3, 4, 5 steps are important questions, but they're not ultimate questions. We want to know for how long the system is safe. Or is it safe for long enough? And then immediately after we have answered the question of safety, the question of stability comes in. So is the process stable? Meaning, will this reactor eventually approach ideal temperature, which is, say, in the middle of the range between 70 and 90? I don't know. I'm just making up numbers. So say it goes to 80, and will it run around 80 in a nice manner, or will it jump over it, going from 85, 75, 85, 75, and so on and so forth? So, again, the questions are entirely answered by the structure of the function f and geometry of the constraint x. So, in the very much the same spirit, we can ask the same question. If you are given a target set xf, you can think of this target set xf as a safe operating region, if you will. And then you ask yourself, what is the set of states which in one step are safe? If we can't answer the question over one step, we can't answer the question over n steps, or for that matter, over infinite number of steps. So, if you think about it, if you write down condition x plus in xf becomes f of x in xf. But this is nothing else than essentially pre-image of xf under function f. And if you still require the states to satisfy constraints x, you have to take intersection. So characterization is much easier. And this object, restricted pre-image of target set xf under function f, this should be a single dot. Doesn't matter. So this is another reason why I wasn't actually happy to share slides a priori, because I'm pretty sure there are typos. And as I give you lectures, I can see some of them and correct in the evening before giving you the link. But in either case, it's under F. Okay, so the question here is that actually one step backward reachable set is nothing else than the pre-image of a target set xf restricted to the constraint. This is precisely the set of all initial conditions which actually remain in one step. First, they satisfy constraint and go to a target set xf. Now, if you look at the polyhedral structure, again, I'm bringing up polyhedral structure for the computations to follow. Can we actually preserve the polyhedral structure? If the system is affine, constraints are polyhedral. Okay, let's just substitute. This is a target set. We want this to belong to that set, so essentially plug in this instead of AX. This is indeed polyhedral. Restricted to the constraint set X, meaning you have to satisfy two sets of linear inequalities, affine inequalities if you will. This is still polyhedral set. So one step backward reachable set in polyhedral set, the setting is polyhedral. So if our object constraints are polyhedral and we propagate this backwards in time for finitely many steps, no matter how large, we'll get polyhedral structure. Now, why polyhedral structure is nice? We characterize these sets by actually storing the corresponding matrices. So there is a way to encode the set inside of the computer, or an algorithm that you come up with. By the same token, you ask n-step backward reachable, but now there is no control to choose. It's only actually to pick an initial condition such that when you evolve dynamics, you satisfy constraints and you land in the target set XF. Do you think the previous argument holds about propagating this one step, in this case backward reachable sets? So if I'm safe for n steps, that means I have to be safe for n minus 1 steps. Because if I wasn't safe for n minus 1 steps, I'm not safe for n steps. I violate the constraints. If I'm safe for n minus 1 steps, I have to be safe for n minus 2 steps, and so on and so forth. So the argument boils down to that you actually can implement dynamic programming recursion, which is very much the same. You iterate these sets, n steps, and this is something which will be your function in MATLAB. We'll have two functions for later on today. Actually, we'll have two functions for control case and two functions for this autonomous case. One of them will be one-step dynamics iterate under constraints, and the other one n-step, where this n-step is nothing else than actually calling the one step several times. So the way lectures are built so that actually you can easily also implement it in the code. And you would get a tube as all this iterates. And then actually you can say I'm safe in n steps if and only if my n-step backward reachable set is non-empty and my initial condition belongs to it. Only for these initial conditions I can guarantee safety. That's all. It's characterization of all initial conditions. If you think about polyhedral case, there is another type. It should be just a D, not okay. So this is unsafe D and this is a safe D. So we don't consider unsafe Ds, only safe Ds. So if you think about this, if you have a polyhedral structure at the kth iterate, you plug in and you get the structure at the k plus 1. It's very much the same argument. You substitute one step backward reachable set, which is a restricted pre-image. You obtain the same description through linear constraints, so it's a polyhedral set. So you can gather these matrices together to form the new set of matrices. Okay. All what you really do, you just plug in these matrices below the matrix C to get the GK, and below D you can put HK minus 1 minus GK. Okay. However, when you do this toolbox, many of these constraints which are described by these linear inequalities might be redundant. The toolbox has an option to remove such rows. So these matrices do not have to grow immediately. So the matrix GK may contain only some of the rows of the previous matrices, and we'll test that numerically. Okay, so the whole point is that we can actually do polyhedral structures in the affine polyhedral case. And with this, I would close the first lecture during the time of the second lecture. So we can start the second lecture. Okay. Now, what would be the next and actually more ambitious question? And your colleague was right. He was just one step forward. So he was talking about stability, but before stability, we want to talk about invariance. Okay, so if you were able to solve the one-step and n-step problems, what is the next and perhaps more ambitious objective? So if you think about this plant, so say you build a nuclear plant, you would like this nuclear plant to be safe during your lifetime. But presumably, if you're a reasonable person, you would like this to be safe during your children's lifetime, and their children's lifetime, and their children's lifetime. So suddenly we are talking about thing working well forever. I think the assumption of being a reasonable person is quite acceptable for 99.99%, maybe higher, of population. But the point is, we start talking about infinite horizon. So we want things to work well over infinite horizon. Now, if things work well over infinite horizon, that essentially means that certain things do not change. Passing to infinity is usually passing to limits. So that's related to the invariance. And of course, convergence is to limit. So for the time being, we recall the system and we have a constraints. And the question is, what is a control invariance set? Okay, I'm just going directly to the question. Now, the notion of a control invariance typically is a notion of something not changing. It's invariant. It doesn't change with time. Yep. Control, it means you selected with the control, intuitively speaking. But let's make this precise. Well, a set omega is a control invariant set if and only if for all states in the set there exists a control such that state control pair satisfy the constraints and successor is still inside of the set omega. So for any point in omega, we can find a control u. Now this u might be function of x, because for all x there exists a u. Okay, u of x such that we satisfy constraints and we are inside of omega. So we remain inside of the same set. Okay, and if you think about the definition of a pre-image, if you take a pre-image of omega and you project it, which is one-step controllable set, it means that omega is a subset of one-step controllable set. So what does it mean when set is a subset of controllable set? It means that actually you can maintain the points in it within itself. If you remember that example we had, let's say we started with the target set -3, 3 and obtained that one-step controllable set was -4, 4. So obviously, to control the states to remain between -3 and 3, we could have done that because it was a subset, yeah? So when we're at 3, let's choose a control, for example, -1, that brings the system to 2. When we're at -3, choose a control +1, that brings the system to -2. And map all other points between -2 and 2. So we remained in -3 and 3. So this is the crucial property. So if you can do it over one step, then you can do it over 2 steps, over 3 steps, over 4 steps. So if I can map a point inside of a set to another point inside of a set which has the same property, I can continue this process. So that means trajectories I can control, I can make sure that these trajectories remain within this set. And this property of control invariance is very important, obviously, for the reason of satisfying constraints. Now the question is, if I can do that over infinite horizon, can I do that in the limit? And for that reason, continuity and closeness of the constraints are important. And in fact, you'll see at a later point that actually it's compactness that we're after. So if you recall, what are the good controls? Well, the good controls, again, it is very much the same control map. First, we have this control invariant set omega. We have one-step controllable set. There exists a u such that we satisfy constraints and we evolve the system to the omega. Because it's a control invariant, it will satisfy this condition. And the set of controls will be non-empty. This is guaranteed to be non-empty because if you assume that this is a control invariant set. Now, can you tell me what would be the simplest control invariant set? Let's go back here. Let's say this constraint set contains point. If I tell you which point it contains, I'll tell you the solution. Okay, can you actually give me the simplest setting for which you can give me a trivial control invariant setting? So say this is a continuous function. You can assume anything you want on function f and on a constraint set y. And you give me the simplest possible control invariant set. Okay, so let's say that function at 0, 0 is equal to 0. Yeah? Which is usual assumption. At equilibrium, you can select the control to keep it at equilibrium. So 0 equals f of 0, 0. And say that 0, 0 belongs to the constraint set y. So it's an admissible point. So what would be then a control invariant set? So if we postulate the set omega to be just a single point 0, is that control invariant? Well, by this definition, it's only one point. So at 0, we can select a control 0. Control satisfy constraints, and f of 0, 0 is 0. So it is a control invariant. So the simplest control invariant sets are controlled equilibria. Typically, when you look at the dynamics, what you get already things in a closed loop form. So they give you, and in many cases, when you consider stability questions, it's usually stabilization of the origin. Okay. Now, this is just to get a feeling. Very much. By now, by showing you these graphs and by later on as you do exercises, not any control function can do. Once you have a control invariant set, do you think you can pick an arbitrary control function to actually make it control invariant? No, you have to select the control function which will be from the given set. Now to have a picture, let me actually go back to the previous lecture very briefly. Okay, I think this will do for a second. So if you wanted to remain, say between -4 and 4, you can't take, now what would be, because this is y and this is x, taking control function would be actually just drawing a graph of a function in this space. And what we said, we can actually pick an affine function in the linear case. But what we're effectively doing, we are fitting a hyperplane in this particular case, or a line, inside of this graph of the set of all admissible controls. So we have to select the control function very, very carefully. At any point in time, when I'm at this point, I cannot choose controls which are outside, even though they satisfy these constraints. Dynamical constraints rules out the controls below. So that's an interval. So very much the same for the control invariance. I'll just flip back to this one. The selection of the control function has to be done carefully. And okay, if you take a polyhedral structure, well, you do one step controllable set. You have a target set Gx, substitute dynamics. Instead of x, put Ax plus Bu, move Gc to the other side. This becomes a polytope. The toolbox will allow you to project these things down. You get this. Now, your condition in the polyhedral case becomes testing whether a polyhedra is a subset of another polyhedra. Importance of this condition is that in a linear case, that can be done by using linear programming, and that will be one of the exercises we'll do. See, in general, when we have this written, it's non-trivial method to test this condition. Okay, because what you would like to do, ideally, you would like to solve an optimization problem which tells you this set has that property or this set doesn't have that property. To do this in a general nonlinear case, you'll need a global optimization. For example, you can take a distance of a function from a set and minimize that over the set. But this is a nasty optimization problem. It's not something that you might be able to even answer without further conditions. In the linear case, however, the condition becomes a simple. And as before, there is an explicit description of this set valued map. So any control function you choose would have to satisfy these inequalities. Okay, it's a nice thing to have. Now, okay, now tell me, what do you know about convexity? This is another thing I have to ask before I make assumptions. Have you had a course on convexity? Okay, you know what is a, okay. How many of you had a class on convexity? Okay, so majority. So you know that actually set can be, polytopic set, for example, can be described by finitely many linear inequalities or as a convex halo of finitely many points. Now, when you have a description of a set, this is just description in terms of the vertices. The toolbox will allow you to actually specify either through convex halo finitely many points or the inequalities. There is something special about affine and convex structure, in this particular case polyhedral structure. If you have, let me just give an illustration, but if you have, for example, in 2 dimensions, let's call this x1, x2, x3, x4, x5. Okay. Now, and let's call this set omega. So the set omega is a convex halo of these 5 points, means everything inside can be generated through, so any point inside of omega, x element omega, is equivalent to say that x is a sum, I equals 1 to 5, lambda I xi, where xi are these points, and each lambda I is greater than 0, and sum I equals 1 to 5, lambda I is equal to 1. This is nothing else than the convex multipliers. So often in probability appear as probability multipliers. So that means if I take the point here, I can decompose this point as a convex combination of the extreme points. Now, if I can any point in this set describe as a convex combination of 5 extreme points, can I actually test control invariance set of this set through some kind of finite means? In other words, would it be enough to test control invariance only at these extreme points or vertices? What do you think? So if we can positively say that each of these points can be controlled to a set omega, can we then assert that actually any other point can be controlled to omega? Answer is yes. And this is precisely because what you're really dealing with, first, if you choose 5 controls which satisfy state constraint, you can multiply by lambda i's and sum it up, because lambda i's sum up to 1 for any convex combination, state constraints or constraints will be satisfied. And if you look at if any of the points goes inside of the target set, because again it's a convex combination, it's going to work. So in the linear case, in the affine case, with polyhedral constraints and description of your control invariance set as a convex hull of a number of points, it's enough to test the condition at each of these points. Now, importance of this actually is that you need to verify finitely many inequalities to establish that the set is a control invariant. That's all what it is. Furthermore, if you make a control at each of these points which works, say you select some controls, U4. So say these controls U1, so at each of the points you assign controls U1, U2, U3, U4, U5, and these controls ensure that AXI plus BUI plus C element omega. Then actually what you can do, you can generate the control at any other point through a convex combination of the controls. Okay, so in other words, selecting and not only testing and selecting these controls, which are good. So testing this condition and selecting these controls can be done by just finding these controls and testing conditions at finitely many points. And this is a big difference. And testing this is, as you'll see in the afternoon, will be just linear programming formulation. It'll just solve linear program at finitely many points. Okay, so that's importance of that. Now, the second question you're going to ask, okay, once I have a control invariant set, I know I can keep the trajectories inside of the set for all times. Then the question is, what kind of control invariant set I would like to have? So, assuming I have one control invariant set, so there exist control invariant sets for the constraints and the dynamics, they don't have to exist. There is no reason for them to exist. That's a property of the dynamics and the geometry of the constraints. And we may, if we have a time, we may set up examples where you'll see that there are no constraints. For certain constraints, there is no invariance. Okay, so the question now arises, if I keep these trajectories for infinitely long, the recursion that I have is very much the same. So if I looked at all initial conditions for which I can actually keep trajectories infinitely long within the constraints, what can I say about its relation to control invariance, to the set of these initial conditions? So typically, what you really want to do, you want to find the maximal control invariance set. And you would like to guess that actually it is the set of all these initial conditions I just described. So you pick an initial condition, you run the trajectories, meaning you run the state and control trajectories, they satisfy constraints through the dynamics, and you take set of all these points, and that would be your maximal control invariance set. Well, actually, it's a kind of tempting to say that such a thing without continuity and compactness, it may fail to be true. So if your system is discontinuous, it may fail. Now, to explain that, let me just point out what's the importance of this closed and continuous. Say this is your x, this is your f of x, and say you take 0, 1, and say your function f of x, let's say you define the function f of x half when x is greater or equal than 0, and f of x is, say, -1 when x is less than 0. Okay, it's a discontinuous function, yeah? And say you start from 1. Okay, from 1 you go to half, to quarter, so on and so forth. So if you start from x naught equals 1, you get the sequence 1, half, quarter. The chalk breaks down after quarter. You get 8, 16, 32, and so on and so forth, yeah? So this sequence goes to 0. For all case, the sequence is inside of the set 0, 1. But the limit of this sequence is 0. Yeah? And the function evaluated at 0 is -1. So at 0 you're driven to -1. In this particular example, discontinuity and openness of the constraints actually removes the consideration that all points which infinitely long stay inside of the set form the maximal control invariant set. So it's drawback of two things. Now, this is just to tell you why essentially even simple things can go wrong. But, okay, if we start from a projection of the constraints, so that would be the set of all x's for which you can find the u to satisfy constraints without any dynamics, and you generate these controllable sets backwards in time. What we know? We know that these sets are monotonic. Okay, so if I can control a set to x0, x0 obviously is going to be bigger than x1. If xk is bigger than xk plus 1, then just using this relation, you figure out that xk plus 2 is bigger than xk plus 1. So they're monotone. Thus, if for some index k you obtain reverse inclusion, then you have equality. This equality essentially then gives you desired invariance condition. And moreover, irrespective of continuity, discontinuity, if you do finitely many iteration, then actually you're fine. On the other hand, for continuous f and compact y, these sets actually, when they converge, will give you maximal control invariant set. Now, this is what I said. Without continuity and compactness, this is not necessarily true. This is a simple example to illustrate the point. Now, a simple condition. Now, of course, these sets can be empty. You may not be able to find the control to maintain the system within the constraints. But simple condition, which you typically, this is if you remember what I started initially, 0, 0, 0 equals 0, 0. You typically assume in control problems a point to which you want to control the system. Such a point makes sense to be controlled if it satisfies constraints. Otherwise, why would I like to control the system outside of the constraints? Not quite a sensible goal. And such a point has to be dynamically consistent. Okay, so for continuous f and compact y, convergence of the controllable sets implies the convergence of the pre-images. Pre-images are effective graphs of the k-step controllable set-valued maps. Because they converge, it means that actually control invariance can be induced by time-invariant feedback. And this is important because if you remember k-step controllability problem, we had a time-varying control policy. So we had to use u0 at x0, u1 at x1, u2 of x2, uk at xk. These were different functions. Function u0, u1, u2, uk. Convergence of this for infinite horizon means that actually we can use just some function u. It doesn't depend on time. It depends only on the points x. Mathematically speaking, the maximal control invariant set is maximal with respect to set inclusion, fixed point of the operator, one-step controllable set. And it's given as this object. Okay. We'll do this. This is continuous compact setting. I don't think that I want to drag you any longer into this. you'll see how these things are computed. I just want to tell you how actually for computation we need to know what happens with polyhedral structure. Again, in the previous lecture, if we had a polyhedral structure of the target set at k minus 1, we knew that one-step controllable set would retain polyhedral structure, and the set-valued map would be also polyhedral. The question that we need to answer is, what happens with the limit? So we know that maximal control invariant set is given as infinite intersection of these controllable sets, and therefore, because I stressed polyhedral sets are described by finitely many linear or affine inequalities, if we take infinitely many, this is not anymore polyhedral. So there is no guarantee, unless our iteration terminates in finite time, which will do experiments, there is no guarantee to obtain polyhedral structure. Okay? Polyhedral structure, however, is guaranteed when the set is finitely determined. The set gets finitely determined when, after the k iterates, you get the reverse inclusion. These steps already give you an idea for algorithm. So what your algorithm would do, you would have a function for one-step controllable set. You would generate the successor, xk plus 1, calling that function. You know you're granted this inclusion by construction of the algorithm. Then you need to test this condition. If this condition is satisfied for some time, you can actually claim you have computed your maximal control invariant set. So it's pretty much just calling one function, sadly enough, in general case, infinitely many times. In many cases, however, and this is what is kind of interesting, in many cases when you have a compactness, these things do get computed in finite time. They do get computed in finite time for many reasons. One of the reasons may be also numerical precision that is used for underlying computations. So when you write a code, you can say x1 minus x2 equals 0 in your code, and your code may never terminate, because two numbers are never the same, especially in the computer. But if you say xk minus 1 less than epsilon, when epsilon is 10 to the minus 18, your code may terminate. So often a lot of tools, especially when it comes down to the computations, do not work with the precise or exact arithmetics. Okay, so even if you work with the exact arithmetics, there may be some other artifacts. But in either case, this is the version from what I wanted to tell you. So there are some properties which guarantee that you get monotonically increasing sets, and that actually your condition for finite termination is relatively easy, and that actually we can also guarantee non-emptiness by checking very simple condition. Okay, so these are more or less all tools we need to iterate. And now in the very much the same spirit, question now for you is, if we have a maximal control invariant set, can we actually stabilize all points from this set? What do you think? If you take the same setting, it's just same constraints, it's a different dynamics, minus 2x plus y. So point 1 gets mapped into minus 2. Point minus 1 gets mapped to 2 before the control is chosen. Your controls are between minus 1 and 1. So if I go from 1, I go to minus 2. Best I can do is to select the control 1 to go to the minus 1. And then from minus 1, I get mapped to 2, choose the control minus. So I generate the limit cycle between minus 1 and 1. So if I start from minus 1, my best control would be to generate this sequence. If I shift this just starting from 1, it would be the other one. This is what is called as a limit cycle. It's just one-dimensional limit cycle. Now, the point that gets often confused, and I think this is very important for you to understand, that maximal control invariant set is not necessarily the maximal stabilizable set. This is related to your question of the stability. So the aspects of safety and stability are two different. You might be able to achieve one goal, while actually you fail to achieve the other one. While for some of the points you might be able to achieve. In this particular case, the boundary of your maximal control invariant sets, points minus 1, 1, are formed by the limit cycle. Any other point in between minus 1 and 1 can be controlled to 0. I suppose you trust me, but let's play a game. Can somebody pick a number between -1 and 1, excluding -1 and 1? And presumably a nice number. Let's say 1 decimal place. Half. Somebody said half, yeah? Okay, so if you give me a half, the system kicks me to -1. I choose the control 1 and I put the system to 0. So let's get more exciting number. Or bigger number in absolute. Any other proposals?
0.8.
0.8. So if you get 0.8, you get -1.6, select the control 1. 0.8 is mapped to 0.6, so you have reduced the norm. So you see that you're gaining stability. From 0.6, you go to -1.2, choose the control 1, go to 0.2. You have reduced the further one. From 0.2, you go to -0.4, choose the control 0.4, you null the system in 3 steps. So, but if you give me 1, the best I can do is just to generate this limit cycle. So I oscillate between the points -1 and 1. Okay, so this is one of the points I do want you to take on and memorize. Okay, so, all right, let's stop here. I'll take the questions, and then later on today we'll install the MPT and close 3-4 slides on positive invariant things and then do computations. Any questions? I know these are not like 9 o'clock morning topics, concepts, especially when there is a guy who speaks strange English, well, good enough English, but I'm in Norway. So just bear with me, wait until you do the exercises, things will start coming together. Two days are hard. These days are hard, but the reasons why these days are hard, I do want to give you structure of these solutions, to explain how the exact solutions will be obtained, and why these solutions, unfortunately, even though we do have computational tools, are applicable only to limited scale of examples. What I didn't tell you, but this is something you'll experience yourself with the code, is that actually, even though these sets may seem nice, they're described by linear inequalities, well, the number of inequalities that you need to describe sets in higher dimensions grows quite badly. So to describe let's say just to describe hypercube or a cube, in 1 dimension is just 2 inequalities, yeah? -1 and 1. In 2, it's 4. In 8 there is 6 points, but essentially we need 6 hyperplanes. So this is 2 to the n. But the number of extreme points of hypercube, it becomes 2 in 1 dimension, 4 in 2 dimension, 8 in 3 dimension. Okay. So one of the things in description of the set, either vertices or hyperplanes explode exponentially. So for that reason, complexity of describing polytopes, even though they're the simplest, possibly simplest form of sets to use for any meaningful computations in control, limits computations to anything, let's say, small to medium-sized problems, where this small or medium size refers to the dimension of the state space. But quite often, a lot of control problems actually do have 3, 4, 5, let's say 10, maybe sometimes 20 dimensions. But don't expect to solve the problems of state of 1,000-dimensional system using these methods. Anyways, you'll see when you do computations that actually things can get very quickly very complicated. But you'll get very nice structures and very nice forms of the sets. Okay, so if there are no further questions, I think it's 3:73, if I'm not mistaken. So usually we'll stay in the afternoon also in this room, but for today it's 3:37. Okay. Any other questions? Anything else you like me to slow down, speed up, disappear from Norway? You're entitled to suggest. I mean, it's a free country after all, and you pass the age of 13. So, all right. If not, I'll see how we did in the afternoon. I'll see how many of you can. Thank you for listening. Thank you.